Hello and welcome to our today's Digital Gateway online event on the showcase Proteus, a platform for monitoring and predicting water quality and availability with Dr. Janek Richter, Paul Schütz, Patrick Preuß, Ludwig Müller and Mika Engels from the University of Cologne. Thanks for having you. I'm Sibylle Tuster. And I'm happy to facilitate this session. I am also a moderator of the GIZ Digital Gateway portal and community, where you find inspiring topics, tools and services, a bunch of information, and last but not least, answers on questions round about digitalization at GIZ. And one of the Digital Gateway services is our online event series taking place every 2 weeks. But let me stop now for today's session and hand over to Janek. Great to have you. Please take over the presentation that I will share with you in a second, and feel free to introduce yourself. The stage is yours. So you should be able to see the slides and to take over. Great.
Thank you great. Thank you very much, Sibylle. Thanks for the nice introduction. And thanks for the opportunity to present our project here on the GIZ Digital Gateway. We will talk a little bit about our university project on Chilean water governance with a Proteus platform, which is basically a project that was initiated by a new teaching offering here at the University of Cologne in the information systems area. First, I would like to introduce the team to you. So who are we? On the right side, you can see Patrick, Ludwig, Mika, and Paul, which are all master students here at the university in their final master's year. And on the left side, you can see myself, Janek Richter. I'm a postdoctoral research fellow here at the Cologne Institute for Information Systems, and I also finished my PhD here in Cologne early 2019, and since then I'm offering teachings here in Cologne in the information systems area. And we initiated a new offering in winter 2019, which is a digital sustainability lab. The objective was that we wanted to offer something where students can learn how to develop innovative digital sustainability solutions. And by using these solutions, addressing the Sustainable Development Goals. And these projects were run in an agile and design-led manner, and we put a very strong focus on creativity and out-of-the-box thinking. And the idea was that the final solution should be a digital artifact in the sustainability space, which consists of a software and hardware component. So, for example, an artifact with sensors, physical equipment, which can manipulate the environment, tangible user interfaces, and so on. And I developed this course together with my colleague, Professor Jan Recker, who's also here, professor at the Institute. So we had a wide area of application domains for these projects. So basically, students could freely decide on which topic they want to address. We had projects on smart ventilation in schools. We had a project on smart food storage for consumers. And we also had a project where we partnered up with the GIZ, who provided a case from the water governance domain in Chile. And this is the project which we want to present today to you. And which I will give now over to the student team, and they will present the project.
Yes, so thank you, Janek, and Before going into details, what we as a student team wanted to solve, I would like to first show you this picture. And one might wonder what this picture actually shows. And this is a lake in Chile. And this lake used to be a crucial water resource, and it dried out by the year of 2018. And we think that this serves as a good reminder that there are regions in the world that struggle with the availability of fresh water, which brings us straight to the problem that we wanted to tackle, or at least try to tackle, and that's about water governance in Chile. We were very fortunate that we could listen carefully to a local expert from a green consulting agency, the Green Factory, and he explained to us the situation in Chile. And especially in rural Chile, there are like 3,000 communities that manage their drinking waters on their own, and that's primarily wells. And there's little to no monitoring of water, either quantity or quality. This affects roughly 3 million people, and this has severe implications, for instance, when droughts do occur. And we thought that maybe if we could increase the availability and transparency of data regarding water, both quality and quantity-wise, we could help these communities to act upon this data. So that was our project goal. As information systems student, we wanted to use our information system skill and create an artifact that provides these help, that is, increase the availability of data, both quantity and quality wise, and enable local communities to act upon this data. Now, what is the solution that we came up with? And we coined it Proteus Platform, and it basically is made up of two things that are meant to work in conjunction. And the first thing is the actual platform. That's a piece of software that allows to gather data from a sensor network, monitor the data, and even provides some kind of forecasts. And a hardware device meant for measuring, Arduino based, and it is equipped with a couple of sensors and is meant to be distributed as a sensor network over huge geospatial distances. Now that was rather abstract. I would like to show you a couple of more in detail information. So let's take a brief look at how these components look from a bird's eye perspective. Now, both the software as well as the hardware artifact are made from different components. Imagine that you are in rural Chile, part of a community, and you want to measure how water quantities and qualities evolve in the wells located in your region. Now, right down here you have a well. This is what a well should be, and you have one of these measuring devices, which we call Proteus meter. And these measuring devices come equipped with certain sensors, and these sensors are, for instance, pH value sensor, or a sensor that measures water temperature or the water level itself, and you hook them up into a well. Now, so these are the sensors hooked neatly into your well, and you attach these measuring device to the well. It comes with additional goodies, like, for instance, a GPS sensor for allowing to figure out where this well is situated. And it also has means of sending data over a radio frequency. Now, there can be multiple sensors depending on what you want to measure. In our case, it were 3: water temperature, pH value, and the water level. And the Proteus meter would measure these things like every 60 seconds. In our case, you can, of course, alter these intervals as you like. And the data packets are sent over the aforementioned radio frequency via a protocol called LoRa, which enables spanning huge distances due to being low powered. And the data packets are picked up by a certain gateway. And I can show you a picture of that in a second. And this gateway forwards the data packets to the actual platform. That's the piece of software that I've been talking about before. It's made from different components, but I think that would be too technical. I'm not going to bore you with those, but I think we should rather take a look at how this platform gives both community members and agents from water agencies the ability to monitor and alter the master data on wells. Now, we would have loved to do an actual live demo like we did back in college, but due to the current coronavirus pandemic, we are unfortunately not able to gather as a group of students, or let alone do that on campus where our prototype is stashed away. So unfortunately, I can only walk you through a couple of screenshots, but that's what I'm going to do now. Like I said, the platform and the hardware device are made from multiple components, both hardware and software-wise. Some of them are very technical and not that interesting, but there are some that are more tangible, like the Arduino, the dashboard, or the admin interface. Now, this box here with the sensors is the actual measuring device, and I can show you a more in-depth view of how this thing looks inside, if you want, in the end. But first, let me show you how this looked in our demo setup back in college. Now, obviously, we didn't have a real well when doing our live demo, so this used to be our simulated well. And the box on the right is the actual measuring device that you would hook up into your well if you were in a rural part of, say, Chile. And so we then used to alter both quality and quantity by adding, for instance, hot acid water. And that was pretty cool, and it showed all up live because there was a LoRa gateway, and we used to run our platform in the cloud, and everything was fancy. Now, unfortunately, we cannot do that live now, but I can show you how the dashboard view looked or would look if you are part of a rural community. And this is it. This is the probably primary source of gathering information on your fleet of wells or measuring devices. And in this case, you can see the well that we are actually inspecting right now, or that a member of the local community will inspect, is situated somewhere in Chile. The measuring device measured a certain pH value, a temperature, and a certain water level. It even displays the water level over time. Now, if one of these things changes, for instance, due to a drought, or in our case, because we poured acid water into our small well, these changes are reflected in real time. So, for instance, you can see that the pH value dropped and the water is now not drinkable anymore. The pH value came into a critical threshold, and therefore it's now displayed in red. Now, this is the primary means of gathering information, but we thought that maybe there is some room for more, and that's why we added a little prediction feature. Now, this is the view that you would get if you wanted to predict the water level in a specific well. This is, in our case, the test well, but it's real data. And you can see, again, the green curve is the actual data, and here's another curve, the yellow one, and it shows a prediction of how the water quantity will develop over time. And you see it actually worked out quite well, but there are some limitations. I will come to that in a second. Now, both the wells and the things that can be measured with them are obviously dynamic. So community 1 has different wells than community 2 and maybe even wants to measure different things. That's why we provided this lightweight administration interface, which allows you to add, delete, and edit wells. Yeah, for instance, you can change the names and you can change diameters, or you can even change what they are measuring. And yeah, that's a nice tool that allows right now to administer your fleet of devices. So that was our brief glimpse at how these, at least the tangible things, look like. I would like to talk a little bit about what we found out and where the limitations are. So first and foremost, our biggest learning was that things like this hardware device that was meant to measure multiple water-related metrics, they can be assembled very easily and very cheaply. We used industrial-grade sensors with an Arduino board, and we didn't have any industrial machinery attend at all. As a group of students, we only had a couple of screwdrivers, and they worked out perfectly well. This implies that one could probably assemble these things in the local areas by the communities themselves and would not have to either buy expensive components or pay a lot of money for companies to assemble them. We also use open source software, so one would not have to pay any bucks at all for industrial software solutions. Speaking of cheap hardware, so this is a basic overview of what we bought. Bear in mind that we bought all these things as private customers from an ordinary electronic online shop in single quantity. If one would buy these things in larger quantities and maybe go for not that high value sensors, these things obviously would get cheaper. And this, by the way, was a kit. So we got 2 Arduinos with 2 LoRa chips and a gateway. So overall, this is affordable for communities in rural areas. Talking a little bit about the contributions. So what we think is that this platform, as a prototype, but it shows that one can derive action from making data more transparent. One could enable more sustainable water resource management, especially because the problem becomes more tangible. And this should, we think, motivate action. And due to the fact that we implemented this prediction mechanism, one could actually help to prepare for such situations in advance and maybe even allow communities to collectively solve problems that arrive. Now, where are the limitations? There are some obvious ones and one not so obvious one. So first and foremost, this has been a lab setup, obviously. You've seen the picture. The cable length was rather limited and we didn't use any renewable power source at all. We basically used ordinary power outlets. And this is something that one would have to take a look at if this was to be deployed in the real world. And not so obvious, but probably the biggest limitation is that the prediction algorithm that we used was a rather trivial one, and it was only a single one. That brings me to the very last slide. How could this thing be extended? And the obvious thing, of course, is to alter and change the way how things are predicted. One could add, for instance, more sophisticated statistical models, or even use machine learning models. And the second thing that we thought would be cool to extend is this could be turned into a platform that not only measures data related to water, but it could measure environmental data in general. So right now the platform is actually built in such a way that it can persist and monitor arbitrary data due to the API design and the internals. But we, of course, only tested this with with these 3 water-related sensors. So one extension would be to, for instance, measure greenhouse gases in a city and pump that into the platform as well.